Welcome to Module 6, Multiple Regression Analysis. For this module, our learning objective is to explain how multiple regressions can be applied to predict an unknown y value founded on a corresponding set of x values, or understand functional association between the dependent and independent variables. Multiple linear regression, or MLR, also called plainly as multiple regression, is a statistical technique that utilizes many explanatory variables to forecast the upshot of a response variable. The purpose of MLR is to demonstrate the linear association between the explanatory or independent variables and response, or the dependent variables. In principle, the multiple regressions are the expansion of ordinary least squares, or OLS regression, since it includes more than one explanatory variable. The multiple linear regression equation is as follows: y is equal to b sub 0 plus b sub 1 times x sub 1 plus b sub 2 x sub 2 plus until b sub p x sub p, where y is the forecasted or expected value of the dependent variable x1 through xp, are p distinct independent or predictor variables. B sub 0 is the value of y when all of the independent variables through x1 through xp are equal to 0. And b sub 1 through b sub p is the calculated regression coefficients. Every regression coefficient denotes alteration in y relative to a one-unit change in the particular independent variable. In the multiple regression situation, b sub 1, for example, is the modification in y relative to one-unit change in x sub 1, considering all independent variables constant, that is, when the residual independent variables are considered at the constant value or are fixed. Once more, statistical measurements can be done to evaluate whether each regression coefficient is considerably different from 0. Multiple regression analysis can be applied to evaluate whether co-founding is present, and since it permits to calculate the correlation between a provided independent variable and the result holding all other variables constant, multiple linear regression also provides a way of attuning for or accounting for probably co-founding variables that have counted in the model. Assuming there is a risk factor or an exposure variable, which is denoted as x sub 1, that is, x sub 1 is obesity or x sub 1 is treatment, and a result or dependent variable which is denoted as y. A simple linear regression equation can be calculated relating the risk factor, the independent variable, to the dependent variable as follows: y is equal to b sub 2 plus b sub 1 times x sub 1, where b sub 1 is the calculated regression coefficient that counts the connection between the risk factor and the result. If one intends to determine whether a third variable, that is age, is a co-founder, the potential co-founder x sub 2 can be denoted and then calculate multiple linear regression equation as follows: y is equal to b sub 2 plus b sub 1 times x sub 1 plus b sub 2 times x sub 2. In the multiple linear regression equation, b sub 1 is the calculated regression coefficient that measures the connection between the risk factor x sub 1 and the result attuned for x sub 2. B sub 2 is the estimated regression coefficient that counts the connection between the probable co-founder and the result. As observed earlier, some researchers evaluate co-founding by measuring how much the regression coefficient related with the risk factor, that is the measure of correlation, varies after attuning for the probable co-founder. In this case, one can compare b sub 1 from the simple linear regression model to B sub 1 from the multiple linear regression model. As a rule of thumb, if the regression coefficient from the simple linear regression model alters by more than 10%, then X sub 2 is said to be a co-founder. When a variable is determined as a co-founder, one can apply multiple linear regression analysis to calculate the relation between the risk factor and the result at tuning for that co-founder. The test of the significance of the regression coefficient related with the risk factor can be utilized to evaluate whether the connection between the risk factor is statistically significant after accounting for one or more co-founding variables. Assuming one intends to measure the relationship between BMI and systolic blood pressure using data gathered in the 7th examination, a sum of N, which is equal to 3,539 study participants, attended the test and their mean systolic blood pressure was 127.3 with a standard deviation of 19.0. The mean BMI in the sample was 28.2 with a standard deviation of 5.3. The simple linear regression analysis is shown in the table. The simple linear regression model is given by y is equal to 108.28 plus 0.67 BMI, where y is the forecasted or expected systolic blood pressure. The regression coefficient correlated with BMI is 0.67, where 1 unit increase in BMI is connected with a 0.67 unit increment in systolic blood pressure. The relationship between BMI and systolic blood pressure is also statistically significant, where P is equal to 0.0001. Assuming one would like to measure whether age, a continuous variable measured in years, and male gender, yes or no, and treatment for hypertension as yes or no are potential co-founders, and if so, fittingly account for this utilizing multiple linear regression analysis. For analytic purposes, treatment for hypertension is coded as 1 as yes and 0 as no. Gender is coded as 1 as male and 0 for female. A multiple regression analysis is displayed in the table as follows. The multiple regression model is given by y is equal to 68.15 plus 0.58 BMI plus 0.65 age plus 0.95 male gender plus 6.44 treatment for hypertension. It can be observed that the connection between BMI and systolic blood pressure is lower, 0.58 versus 0.67, after attuning for age, gender, and treatment for hypertension. BMI stays statistically significant connected with systolic blood pressure, with P is equal to 0.0001, but the magnitude of the correlation is lesser after adjustment. The regression coefficient declined by 13%. Some researchers calculate the percent change utilizing the adjusted coefficient as the primary value since it is theoretically unconfounded. With this technique, the percent change would be equal to 0.09 divided by 0.58, which is equal to 15.5%. Both techniques are applied and the outcome are usually quite the same. Applying the informal 10% rule, that is, a change in the coefficient in either way by 10% or more, the criteria for co-founding is determined. Hence, portion of the connection between BMI and systolic blood pressure is discussed by age, gender, and treatment for hypertension. This implies a helpful means of determining co-founding. Commonly, we attempt to set up the relationship between a primordial risk factor and given a result subsequent to the adapting to at least one other risk factors. One valuable procedure is to utilize various multiple regression models to look at the relationship between the essential risk factor and the result prior and then afterward, including conceivable confounding factors. If the incorporation of a potential confounding variable in the model causes the relationship between the essential risk factor and the result to change by 10% or more, then at that point, the extra factor is co-founder. Evaluating just the p-values proposes that these three independent variables are similarly statistically significant. The extent of the t-statistics gives a way to pass judgment on the overall significance of the independent variables. In this model, age is the main independent variable, succeeded by BMI, treatment for hypertension, and afterward males. Males do not arrive at statistical significance of p is equal to 0.1133 in the multiple regression model. A few researchers contend that whether or not a critical variable, for example, gender, arrives at statistical significance, it ought to be held in the model to control conceivable confounding. Different examiners just hold statistically significant variables. This is yet another example of the complexity involved in multivariable modeling. The multiple regression model estimates the association between BMI and systolic multiple regression model that accounts for differences in systolic blood pressure due to age, gender, and treatment for hypertension. This is one more illustration of the intricacy associated with multivariable modeling. The multiple regression model gauges the relationship among BMI and systolic multiple regression model that records for variation in systolic blood pressure because age, sex, and treatment for hypertension. A 1-unit increment in BMI is related with a 0.58 unit raise in systolic blood pressure, holding age, sex, and treatment for hypertension consistent. Each extra year older is related with a 0.65 unit increment in the systolic blood pressure, holding BMI, sex, and treatment for hypertension consistent. Men have higher systolic blood pressures by about 0.94 unit, holding BMI, age, and treatment for hypertension constant. And individuals on treatment for hypertension have gender systolic blood pressures by roughly 6.44 units, holding BMI, age, and gender constant. The multiple regression equation can be applied to calculate systolic blood pressure as a function of a research participant's BMI, age, gender, and treatment for hypertension status. For example, one can calculate the blood pressure of a 50-year-old male with a BMI of 25 who is not on treatment for hypertension as follows. Y is equal to 68.15 plus 0.58 times 25 plus 0.65 times 50 plus 0.94 times 1 plus 6.6 times 0, which is equal to 116.1. We can estimate the blood pressure of a 50-year-old female with a BMI of 25 who is on treatment for hypertension as follows. Y is equal to 68.15 plus 0.58 times 25 plus 0.65 times 50 plus 0.94 times 0 plus 6.44 times 1, which is equal to 121.59.